Hello, everyone. and Welcome to another session with me on AI/ML inference and training. Uh, Today, I will be focusing on the inference benchmark, and it is for open source LLMs like Mistral, Falcon, and Llama 2. So I will just go over some of the key points. I will be sharing some results, and I will have a short demo how we have trained Llama 2 model and then deployed it for inference on OCI A10, NVIDIA A10 GPUs. So ask me anything through the question tab, and I will answer them after the presentation. And then I have also included my contact, so please feel free to ask me afterwards also. So without further ado, I will begin the presentation. So it is having three sections. One is introduction to the open source large language models that we have used, and then the benchmarking process for Llama 2, 7 billion and 70 billion parameter models, and then benchmarking process for Mistral 7B. One of the things that I want to share is that we are focusing on large language models. It is not on everyday AI, not on the classic AI models. So this inference is only focused on generative AI. So just setting the stage, because with everyday AI or classic AI, you can run the inference on CPUs, GPUs. But with generative AI and with anything which is in the range of 7 billion to whatever, 1 trillion parameters, you will need GPUs. And I will go over some of the GPU families that we have tested these models on. So one of the things I just want to share with you, what I am seeing in the industry, that we are seeing a fundamental paradigm shift in computing. So now our LLMs, foundational models, have become the compute. And in that, you are actually encapsulating the underlying hardware and software. And the way you are interacting with this computing platform is using natural languages like English. So basically, you are programming this computing platform to get the desired output using your natural language. And then that output can be interacting with databases, other applications, or any other business systems. And this is where the inference is happening, all right? How you are getting the desired output using natural language. So one of the things when we talk about inferencing benchmark, there are two distinct type of benchmarks or categories of benchmark. One is benchmarking the underlying infrastructure that you are using for training and inference. And those benchmark standards, or one of the most important benchmark standard, is from ML Commons. So we have run ML perf across our hardware stack for today's inference benchmarking, we are not focusing on the infrastructure. We will have a follow-up session only focusing on the infrastructure benchmark. This benchmark is more at the higher level, where we are benchmarking the quality of the LLM after you train it and use it for inference. So here, what we are doing is that in this presentation, we are focusing on the optimization and benchmarking details that are highlighting the importance of model sharding, tensor parallelism, and the efficient use of underlying hardware resources for managing the computational demands. And then this performance of this model can significantly vary depending upon what hardware you are using underneath. And the model architecture and the inference strategies you have employed, whether you are doing quantizing or whether you are doing some type of sparsity, optimization. So this is what. So this is a table where we have actually used higher level benchmarks like MMLU, HelaSwag, PK, NQ, trivia question and answer, human eval from Stanford, math, and GSM 8K. And of course, here the table is only focusing on smaller open source models like Llama 7B, 13B, and Code Llama 7B and Mistral 7B. What we have seen that in some of the benchmarks, Mistral 7B is actually better than Llama 13B. The Code Llama 7B I have used fine-tuned. It is not pre-trained. And in the fine-tuning, of course, some of these numbers are not very good, maybe because of the data set that I have used. So it is actually limited by the quality of the data set that I have used for the fine-tuning. So another thing I just want to highlight here, that our inference is not just a chatbot. I will have a demo of the chatbot, but the actual value lies in how these inference agents are plugged in to bigger application. So say we are working with a travel agent AI bot, and only thing you should be interacting with the bot using your natural language, and you should say, book me a flight to Seattle, and it will understand and interprets the prompt. It should have access to your calendar and other systems, so it can determine the necessary actions. It retrieves, say, your calendar data from Outlook, then it executes the actions. It has integration with, say, American Airlines or Sabre or any other travel agency application, and then it will get back with your itinerary after it books the flight. So some of the things with our open source language models, what I have said, that it is pivotal in natural language processing. NLP actually come to fruition with LLM. So one of the things what we do whenever we go through this benchmarking, we actually choose an LLM and we see that why it is important to us, why it is important for your application, why you want to use it as an agent. And then we go to the next step, that what are the key features which are already existing in these pre-trained models. Like for Llama 2 and Mistral, we know that they have been trained on a vast data set and knowledge base, and it has some context understanding, and it can generate human-like text, right? And then about the applications, what we see that we are having use cases, and I will share the use cases separately with you in a follow-up email from ODSC. So what we see that these applications can be used both vertically for very, very industry specific use cases, or it can be used in a horizontal manner, like customer service, any content creation or data analysis across all the verticals. So once you know that why you want to use the LLM agent, then you can focus on some of the uh, benchmark parameters that you want to do. So if it is, say, if you are doing content creation, then you may not have to benchmark it on the math capabilities, but you should be benchmarking it in the human eval, matrix. So as I have said, for this, if you want to if you want to see that what is the role of inference benchmarking, it is across three categories. It is actually defining the inference benchmarking for your use cases, for your purpose. Then what is the importance in deployment, whether you want it to be uh, offline or real time, and what are some of the optimal performance that you need, so that you can choose also your underlying infrastructure hardware, and whether you have to configure them accordingly. And then of course you have to also consider the challenges and other concerns, like hardware compatibility, model size, and the inference speed. So for the Llama 2, again, we have taken the or we are highlighting the top 3 considerations, that what is the inference speed, what is the resource utilization during inference, and how we are assessing the accuracy. So what is happening here is that we have actually benchmarked it across NVIDIA A10, A100. We have also done some H100s, but H100s is, it is completely underutilized when you are running a 7 billion or a 70 billion parameter on H100. So I will not go over the H100 results. And then we have also benchmarked it on L40S. Though I am not going over the training here, we actually trained on both A100 and L40S, and we have done inference then on A10, A100, and L40S. And we have used open source Kubernetes for the deployment. We have used Kubeflow, and we have also used NVIDIA's Triton. While we were doing that, we were keeping an eye on the resource utilization. It is not only the GPU utilization, but it is also how much power it is consuming. So we have telemetry into OCI Oracle cloud infrastructure. So we have actually measured those telemetry and made sure that we are choosing the optimal hardware for these benchmarks. And then of course we have assessed the accuracy of the output, using one of those earlier benchmarks that I have shown. So this is what I will be sharing the slide, and you can see that it is running on 1 minute. So yep. So we have actually used a batch size from 1 to 10 to 24, and we have measured the GPU percentage used. We have measured the tensor core activity or the active tensor core usage. We have measured the active GPU memory usage, and we have also measured the GPU power for running this inference benchmark. And of course, we want to run it consistently using batch 1 to 1024. So here are the results which I have included here. So if we go back, you can see that the active GPU usage, the average is 35%. It can go as low as 6% to as high as 67%. For some of the initial batches, the tensor core activity is actually 0%, and then it hardly goes over 2%. And the GPU memory, we have used a 100 with 40 gigs. So 40 gigs with each A100, and we have 8 of them. So it is around 4%, and this is only because it is a 70 billion parameter model. And then the GPU power is our GPU power is capped at 200 watts, and we are using around 173 watts. And then if you aggregate all the GPUs, it is around 47% of all the GPU power that we have. So then we have some, we have some results with here, what I am sharing. So here is the NVIDIA SMI, which is actually calculating. It is on the left-hand side. It is actually calculating the power and memory usage and all those hardware-specific things. And then on the right side, we are running the batch, and we are seeing how it is performing. Here we are using a sequence length of 10, and we are having n run parameter of 10 here. So after this, what we have seen, we are also measuring the average tokens per second, and with the decoder, what we are seeing at the batch 1024, we are reaching an average of 4,280 tokens per second. So and I will also show you, demo you one where I will also show you that how we are measuring the latency. So So if you have a Llama 2 inference which you can get from Hugging Face, and you can run these commands, and you can actually run a 70 billion Llama 2 with Hugging Face chat inference on OCI or in any other place where you have GPU, NVIDIA GPUs. So this is the text generation interface which we have used. You can see and you can plot and see that what is the throughput over the latency that you are getting. And I will show it to you, but we also, this is a chatbot that we have, with Hugging Face chat GPT, which we have used. And then what we have done is that on the side, we are actually calculating, that how much time it is taking to come up with the answer. So before going to that, if you want, I can show you, I can show you 1 minute. Can you see my screen here? If you can see my screen here actually what I am doing is I am typing a thing that what is dynamic routing gateway on Oracle Cloud infrastructure. And you can see here on the right hand, upper side, that how much time it is taking. And here is the answer that it is, that we are getting from here. So again, we have an upper limit of 7.2 seconds, and we are just seeing how much time it takes to, come up with an answer. And some of the answers are right, and some of the answers are not, completely accurate, but it gives a general idea, of what you are asking. I'm going back to my presentation. Okay, next one. Okay, so here what we are showing is that we did the inference on A10, NVIDIA A10. On the left-hand side, we have what the shape has. It is a bare metal, so it has actually 4 A10s, 48 GB GPU memory, and we have used the same Llama 2 70 billion chat, and this is what we are getting. We are getting throughput per second as we are using more, so this is where we are seeing that throughput and latency is actually, merging, and it is for per batch size. So obviously, as we are increasing the inference batch size, we are getting a better throughput, and the latency is of course increasing. So what we have seen that we are getting an optimal performance till the batch size of 16. So this is where we are getting more token and less latency as an output. We did the same inference on L40S, and we have actually also 1 minute. So here actually we are seeing it is on the back side of this, we are seeing the best value around 32 batch size. And then of course we have seen that how they are across other, Ampere, Intel, AMD, and NVIDIA A10, and we have compared them with L40S. So what we have seen that for the price performance, L40S is the best GPU that you can use for any of the Llama 2 family models. So these are the raw data. So if you are running it, this is the best runs that we have. So you can actually compare your raw data with ours and see that how your infrastructure is performing. This is a Llama 2 7 billion benchmark, and of course here we are seeing the best price performance with our OCI VM, the virtual GPU A10 shape, and we are only using one A10 GPUs. So one of the things that what we did, we actually run this to study the 4A 140 GB GPUs with various prompt lengths to assess performance. So what we have seen with 1,500 input tokens and 100 output tokens, the base time was recorded at 7.4 seconds with up to 1.1 RPS before latency started deteriorating. And with another setup with 50 input tokens and 500 output tokens, we have seen the best response time of 33 seconds, maintaining up to 0.8 RPS before facing any latency issues. So we have used some performance optimization techniques that we used with our PyTorch CUDA on our OCI cloud GPUs. So what we have done is that we have sharded the parameter and activation. We have used input sharding and the use of optimizer states and gradients sharding, so that we can maximize the device memory utilization and reduce any communication overhead. So and actually we do this typically for our bigger model of GPT-3 sizes, like 250 billion parameters, but we have also used it here. And then we have done inference optimization techniques, we have used PyTorch and the CUDA libraries, and we have achieved 29 millisecond per token on 8 NVIDIA A100 GPUs with 40 gig memory. We have taken a slightly different approach for Mistral's Heaven B retrained model. One of the things that we have done here, that we have focused on the distinctive features of Mistral's Heaven B. We have some of our inference use cases, which I will follow up with you guys. and then we have actually worked with our other teams to see that how those use cases work across our across our business units. So here we have only done it on A10 mostly, because 7B, for us 7B, our A100s was overkill. And then what we have done is the actual benchmark. We have done it on A100, but the best price performance is on A10 24GB GPUs. We have used it with 1500 input tokens and 100 output tokens. And we have some heavy use cases with 50 input tokens and 500 output tokens. Again, we have measured it on inference speed. We have seen the underlying resource utilization, and of course, we made sure that we assess the accuracy. So the performance, what we have seen on A100 is that it achieved a response time of 2.3 seconds for 1500 input plus 10 output tokens, and with a throughput of up to 2.8 RPS for 50 input and 500 output tokens. The best response was at 9.7 seconds, reaching up to 1.5 RPS. When we ran it on A10, the performance was degraded slightly by 0.23%. So when we went back and we checked, we saw that the A100s were typically underutilized, and the best price performance we are getting with A10 virtual machine with two A10 GPUs, 24 GB memory each. So some of the model efficiency and innovations we used for Mistral 7B is, it is actually designed with GQA, which is group query attention, and also sliding window attention. So it actually increases its inference speed and ability to handle longer sequence efficiently. What we have seen that it continuously outperforms the Llama to 13 billion across all benchmarks, and it is comparable to or it can surpass the Llama 134 billion parameter in many benchmarks if we do code mathematics and reasoning tasks. Mistral 7B's performance equates to that of a much larger model, because it is very effective in delivering higher efficiency on reasoning compression and any math reasoning task. So we are seeing a better performant model with less parameter, which requires less hardware footprint. What is okay? So the deployment and fine tuning, we have taken it from Hugging Face, and we run it on our on our GPU shapes, and right now we are testing it out on NVIDIA L4. So it is a much more compact GPU with a very low power requirement. So you can actually put it into edge, into means you can have a use case for a hybrid cloud where you are doing training in the cloud core using A100s, H100s, and then in a multi-agent scenario you can also train and deploy these smaller models at the edge. So this is the link where you can go and find all the test stuff. It is published by Mistral AI. We actually work with them also, and you can see that the MMLU, the understanding the multimodal language understanding, knowledge, reasoning, and comprehension, how how Mistral is comparable to Llama 2 and Llama 1, and how it is beating, some of them. About this, and you can follow up with me if you have any questions. So I think we have another 20 minutes that we can go to questions if you have any.